Yes, so let me introduce Ryan Kavanagh from Université de Québec et Montréal. Please take it away.
Hi, so my name is... Better? Yeah, so hi, my name is Ryan Kavanagh, and I'm very excited to be talking to you today about message observing sessions. And this is joint work with Brigitte Pientka. So communicating systems are ubiquitous. We find them everywhere from the Internet of Things, to the cloud, to the software that runs on our phones, and that powers the modern internet, like web and email servers. And by communicating system, I just mean a coherent system where the individual components interact with each other through communication. So for example, you can think about the interactions between your web browser and a web server. And communicating systems only work if all the components interact and communicate with each other according to protocols, which are sets of rules that say which messages can be sent and when. And miscommunication is very costly. So to take a particularly notorious example, a few years ago there was the Heartbleed vulnerability that was caused by a bad implementation of the TLS heartbeat protocol in OpenSSL. And it affected all sorts of industrial entities, and it also caused the leak of 900 social insurance numbers from the Canada Revenue Agency. And to put this into perspective, it cost an estimated $500 million to address. Concurrent systems are notoriously difficult to debug, and so what we'd like to be able to do is we'd like to be able to statically guarantee that our programs communicate correctly. And if we're to ensure that our programs have the behaviors we want, we need to be able to precisely specify these behaviors. Fortunately, we already have some technologies that let us do so. In particular, session types let us encode communication protocols at the type level. And then a session-typed language statically guarantees that a program is going to communicate according to its protocols. And there are two main varieties of session types. So multi-party session types let us specify communicating systems top-down. So we can specify all sorts of interactions between collections of processes at a time, but the catch is multi-party session types typically aren't compositional. It's really a global approach where we must specify the entire system at once. In contrast, we have binary session types that let us specify systems bottom-up. So they're compositional, they have all sorts of interesting varieties, but the catch is we can only specify local behaviors between pairs of processes, so it's a very local approach. And so this motivates an obvious research question. Can you have the best of both worlds? So I'd like to be able to specify global properties, as in multi-party session types, but still have some kind of compositional system, as in the binary session type world. And of course, I wouldn't ask this question if I couldn't answer it. So today we'll see how we can get compositionality and global properties in a binary session type setting. So let's kind of set the stage. What do I mean by a communicating system? Well, I mean a collection of processes that interact with each other through communication. So I'm going to treat a process as some kind of black box. And it's going to communicate over wires that are called channels. And communication on a channel must respect a protocol. That's to say, some set of rules that say which messages can be sent and when. And protocols can evolve over the course of a computation to allow for different kinds of messages. And so we're also going to assume a client-server architecture, where every process is going to be a server for some distinguished service. And it's going to be a client of some number of services. So here, graphically, I've put the server channel on the right, and the channels of which I'm a client on the left. And we can use a bit of syntax that I've put at the bottom of the slide to kind of summarize this graphical notation, where I'll put the channels that I'm a client of in square brackets, and I'll put the channel that I'm a server for in parentheses. And I use this C:(A) notation to mean the protocol for the channel C is A. So this is a session type here. And a recurring example throughout this talk that's going to really illustrate some of the key ideas is the bitstream protocol. So it's a recursive protocol that's going to say I can send a bit 0 followed by a bitstream, so that's this B0 : bits, or I can send you a bit 1 followed by a bitstream. And an example of communication that satisfies bits is this bit 0 followed by bit 1 followed by a bit 0 and a bit 0 and so on and so forth. And we can deal with all sorts of more interesting protocols like queues and stacks and auctions, but bits are going to be sufficient to illustrate some of the key ideas. And a natural thing we might want to do is we might want to specify a process that flips bits. So let's consider this process F. Our specification is it's going to be a client of some channel I satisfying the bitstream protocol, and it's going to be a provider for a channel O satisfying the bitstream protocol. And what f is going to do is it's going to sit there listening on the channel I. And suppose a bit 0 comes along. Well, it'll take the 0 branch, it'll send a bit 1 out on O, and then it will recurse, and then it will sit there listening on I. And the problem is the specification doesn't actually specify or enforce bit flipping, right? The identity process on bits also satisfies this specification. In fact, there are infinitely many processes that satisfy the specification on the slide. And the problem here is that traditional binary session types, they're too local. They don't give us a means of specifying relationships between communications on different channels. And so our contribution is a language called MOST that lets us compositionally specify communication protocols that depend on communications on other channels. And compositionality is important because we want to be able to specify programs bottom up. We want to reason modularly about our programs. We don't have to specify the entire system at once. And we want to be able to depend on communications that occur on other channels because we want to be able to specify things like input-output behaviors. And MOST has 3 key ingredients. So we introduce some novel syntax that lets us use type-level computation to specify these communication protocols. And then we give an interesting novel semantic framework for explaining what it means to have a protocol that has dependency, right? And then finally, we give a static type checking algorithm that says, given a specification, does my process, my program, actually satisfy that specification? So what does most syntax look like? Well, we have all of the binary session types that we know and love. So for example, we retain labeled choice. We saw an example of this with the bits protocol. So a labeled choice says, well, I can send you a label L, followed by a communication that satisfies A. Or I can send you a label R, followed by a communication that satisfies B. Right? So the bitstream protocol is this. We send you a bit 0, followed by a bitstream, or I send you a bit 1, followed by a bitstream. And now the novel part is we introduce this kind of big elimination, this type-level process that's going to observe some channel C, and then do something, give us a protocol based on what it observes on C. And so the operational intuition here is that this type is going to reduce to the type A if a label L is observed on C, and it'll reduce to B if a label R is observed on C. And we can have we have similar constructions for observing termination, for observing channel transmission, and so on and so forth. See the paper, the details are all there. So how can we use this to specify bit flipping? Well, if we remember our original bitstream protocol, we can define a bit flipping protocol that uses this big elim. So relative to some channel I of type bits, we're going to define a type called bits flip I. And it's going to be a case analysis on I, and it's going to say, if I observe a bit 0 on I, then I'll give you a unary choice where the only thing you can send is the bit 1, followed by something that satisfies the bits flip protocol. And if you happen to observe a bit 1 on I, then the protocol becomes this unary choice where the only thing you can send out is a bit 0, followed by communication that satisfies the bits flip protocol. And so now what we can do is we can revise our specification and change the type of O from being just bits to being this bits flip I protocol. And we can use this technique to specify any sort of stream, transducer, or multiplexer. In principle, you could use it to specify, for example, the results of DNS queries after doing a DNS zone transfer. You could use it to specify proxies and so on and so forth. And here I want to point out that the protocol, it really looks a whole lot like the implementation of the bit flipping process. That happens to be an accident. It's a really simple process, and a really simple protocol. There's not a whole lot you can do there. But if you look in the paper, for example, we specify a fair auction, where the specification and the implementation are really quite different. And so the first key insight is that we can specify these kinds of dependent protocols using a very restricted form of type-level computation, where we're going to lift a section of the process layer that does observation, that does message observation, up to the type level to kind of programmatically specify protocols. Now, one of the things we were after is a compositional system. So how can we reason about process compositions? So a natural thing we might want to do is we might want to chain 2 bit flipping processes together. So here I have a bit flipping process on the left. It's a client of a channel I, and it's going to be a server for some channel M that satisfies bits flip I. And let's suppose I want to feed that channel into a second bit flipping process. That's going to be a server for a channel O of type ID bits, where ID bits just says, well, I'm going to give you exactly the same thing that came in on I. And we can implement it in the same way as we implemented bits flip using this big lim. Well, if we want to reason compositionally, we'd like to be able to reason about the whole thing in terms of the specifications of the parts. So let's zoom in on the right process here, the right bit flipping process. Well, we notice that we've got this kind of issue here, where the specification depends on this channel that the process doesn't have access to. The specification of M and of O, mentions this ambient channel I that F doesn't have access to. And so what we need to do is we need to extend our specifications to track assumptions that we make about the ambient environment where we live. This helps ensure that the types remain well formed. Informally, what this means is the process has a given behavior provided the environment behaves according to the types in this ambient context that I've put in curly braces. You can also give it kind of a rely guarantee interpretation where you think, well, relying on the fact that the environment behaves according to the specification, I guarantee that my process will behave according to the types in my spec. So what does this all mean? I've given you some new syntax and some informal intuition. How can we make it precise? Well, we give our language a denotational semantics where the processes are going to denote sets of traces of messages, so things that can be sent back and forth. So if you consider the bit flipping process on M and O, well, it represents a set of traces. For example, the first trace says, if I receive a bit 0 on M, then the process will send a bit 1 on O, and so on and so forth. Dually, if it received a bit 1 on M, then it'll send out a bit 0 on O, and so on and so forth, right? So we have a different trace for every possible execution. And then what a specification denotes is also a set of traces that are allowed by the specification, and we need to account for these ambient assumptions. So we're going to add in these special elements that say we're going to rely on these behaviors in the environment. So for example, think back to the rightmost process in the composition. It had this ambient channel I, and it said I was a client of a channel M of type bits flip and a provider of O of type ID bits. Well, an example trace we could have is the trace we have here that says, assuming some bit 0 goes by on I, then the process is allowed to receive a bit 1 on M, and then allowed to send a bit 0 out on O. So it really just specifies which behaviors are allowed. So how do we type check? How do we statically ensure that our processes satisfy their specifications? Well, we give a recursive algorithm in the paper that recurses on the structure of the processes and the specifications. And what it does is, as it checks the process, it's going to generate a set of constraints on the environment. So some set of constraints T, it's going to be an output of the algorithm, of the typing judgment. And then when we come to a case where we need to type check a composition, well, from the recursive calls, we're going to get 2 sets of constraints, and we're only going to allow the composition if each process satisfies the constraints that the other imposes on it. So it's really a constraint generation and constraint checking algorithm. And our type checking algorithm satisfies a soundness property that basically says it's correct. So if a process type checks against its specification, then all of the traces that the process has are amongst those that are allowed by the spec. Remember that the spec gave you a set of allowed traces, so the type checking algorithm basically says if it type checks, all of the behaviors are amongst those allowed by the specification. So the algorithm is in some sense correct. Now, most is not the first dependent session type systems. There are others, for example, value-dependent session types and label-dependent session types by Peter Tiemann in the back. And these session type systems allow for dependencies on previous messages sent on the current channel. And the key difference with most is we allow for dependencies between different channels. So instead of saying we can only depend on what previously went forth on this given channel, we're going to allow you to relate communications on different channels. There are also, of course, multi-party session types, which allow you to specify these kinds of rich interactions, but again, the catch is it's really a top-down approach, it's not compositional. So most is really the basis for a whole lot of future work. So it's a linear type system, and so one of the things that would be nice to do is be able to introduce sharing so that we can specify and verify shared services, like, for example, databases or shared data structures. It would be nice to have a subtyping relation that lets us compose processes where the 2 types are not equal on the nose. At the moment, we require that if you compose things, they must have exactly the common type. This is a bit restrictive. We'd like to be able to relax this. Of course, it would be nice to have a compiler so we can do case studies, play around with this. And one of the things I'm interested in is how can we characterize this expressiveness gap between most and multi-party session types. Multi-party session types are more expressive than most. We have more restrictions, but how can we pinpoint where is that demarcating line? And so with that, I'd like to thank you for listening to the talk, and I'm happy to take any questions.
Okay.
Thanks. Very cool work and good talk. Thank you.
Thanks.
So in multi-party session types, the key thing is that the global types needs to be well formed.
Yes.
And everything depends on that, really.
Yes.
So what's the corresponding ingredient in your work?
The corresponding ingredient in our work. So we do have. We check well-formedness of types during the type checking algorithms. So you could give some kind of ill-formed spec. We don't, a priori have a well-formedness condition on types. Originally, in a prior version of this work, there was a judgment that said, is this type well-formed given some other context of types? That ended up being a bit superfluous. It just made the theory a bit more complicated. Now we basically say you can write some stuff down, and if it manages to pass through the type checking algorithm, you're okay. And semantically, this is perfectly fine because, if the semantics says your things are ill-defined, the type checking algorithm won't be able to check it anyways. Does that work out?
Well, thank you for the talk. That was very nice. I was wondering about the semantics that you presented.
Yes.
Is that a synchronous semantics?
Yes, it's synchronous.
So do you see any trouble in adjusting stuff for asynchronous semantics?
No, not at all. So I didn't mention it. So our traces have a notion of binding that I didn't get into that lets us easily model channel transmission. And basically, you could encode an asynchronous semantics using continuation channels. So basically, you add a new binding operator and you encode continuation channels that way so you can get asynchrony. So there's a section in the paper where we discuss how can you extend this to handle asynchronous communication. It's straightforward. The system used to be asynchronous, but just to make it clearer, we went for a synchronous version and paired it back.
Can I ask another one?
Sure.
Hi. Thanks, Ryan, for the talk. So I'm wondering about the experience of writing programs in MOST. So especially now that you have type-level computations and constraints on types,
yes.
Is type checking still decidable? Are there cases where you cannot have a type checker algorithm to work with your programs?
So it's all decidable. It's expensive. When we check composition, I haven't done the complexity analysis, but when you go to check composition, you need to check the constraints, and that's done with a predicate on sets of traces, and that just is exponential blow-up. So I sketched in the paper some ideas for how to make this more tame. There's some data structures you could consider that I mentioned, but there's no implementation as of yet. This is still future work.
Hi, thank you so much for the talk. So I'm not an expert on session types, but I was wondering if your type system could capture scenarios where the process could choose to send or not send to a channel depending on the value received.
That we cannot do.
Okay, I see.
We have, in one of the extensions, we allow for a certain form of non-determinism, a select statement like go, but we don't have something. You could maybe encode that. You could maybe, not on the same channel, but you could have something similar on different channels.
I think this is a short one. So your example was about a unidirectional protocol, right? So what would change for a bidirectional one? Or
Absolutely nothing.
Nothing.
It works just as well. It just happens the example is sufficiently simple for it.
So you can put the eliminations in any order on any channel in that specification.
Completely bidirectional
All right.
communication.
Thanks.
It's a normal binary session type system.
Great. Let's thank Ryan.